Guys, so Francesco here has come over from London, and he's going to talk to us about Agda. Agda is one of the few programming languages that takes types even more seriously than Haskell does. I think I saw some code in Agda where if you want to do division, you need to prove that your divisor is not 0. Of course. Why not? And he's going to show us how you can implement a simple lambda calculus interpreter in Agda, and then write an optimization, and then you can actually prove that optimization correct. It'll depend on time constraints, but he's got a couple of steps, and so this will be a sort of introductory walk through Agda. Francesco, everyone.
Okay, can you hear this? Is it going through? All right, so thanks, Anthony, for the nice talk. I probably have to. This is not. Okay, I'll just do this. Right, okay. So yes, I'm Francesco, and today I will talk you. This talk is not about the real world, by the way. So it's kind of about a language which is trying to make it to the real world, but it's not quite there yet. But I think it's very interesting, and I hope I get you curious about it. And how many of you have heard about Agda before? Like, okay. So how many of you have used Agda? Okay. So it's a functional programming language that kind of grew out of the Haskell community. So that's why I'm here in the Haskell meetup talking about another functional programming language. And its main feature is really the type system. So it goes further than Haskell in quite a profound way. It's not kind of features bolted on to Haskell type system. It's kind of a step forward in a way. These kind of languages, you might have heard Coq or Isabelle. It's kind of a class of languages. And they're mainly used right now by mathematicians because they're so powerful that they can be used to formalize mathematics. Okay, but I think there is great opportunity for them to be used in software engineering. So that's kind of my focus here, not mathematics, but yes, software. And so what I'm going to do, as Ryan said, is define this very simple language and write a type checker for it in Agda in a way that we couldn't do in Haskell. And if we have time, which I don't think we will, but if the talk goes really smoothly, maybe we will. I'm going to write a simple optimization and prove it correct. And the way we write the type checker is important for the next step. And it's going to be live coding, so it's dangerous. So forgive any mistakes that I make, but I think it's kind of less boring that way. Right, so yeah, I want to give credit where it's due. So the type checking example is kind of famous in a way, and it was introduced by McBride and McKenna in this very nice paper, actually. So if you're interested in dependent types, you should check that out. The second part of the talk is taken from a talk given by Adam Kripala. And this is kind of a plug to tell you about this book, which is another great resource for dependent types. So maybe I'll put up the slides online, but these are two great links. Okay, so this is Emacs, okay? And to use Agda, you have to use Emacs, which is a great thing. And what I have up here is kind of the window showing Agda stuff. On the bottom right, I've got this buffer showing what I'm doing with Emacs. It's not very important, but I thought it might be useful. And first, we'll do something we can do in Haskell. So we're going to define natural numbers. Right. So what I'm doing here is that I'm continuously reloading the file. And it's an interactive mode, so we can load the file and do a lot of other things with it. So in Haskell, what we would have is this. A natural number is either 0 or the successor of another natural number. It's very straightforward, maybe the simplest kind of inductive definition. And in Agda, we're basically saying the same thing more explicitly. So the first thing that we're doing explicitly is that these are the data constructors, and we're writing down their types manually. So when we write this in Haskell, what will actually happen is that 0 is of type nat, and sac is a function, is a data constructor taking a natural number and forming a new one. In Agda, we have to write this explicitly. And this is because this data type is kind of simple, but there are more complex data types in Agda that need explicit type signatures. If you have used GADTs in Haskell, the syntax is very similar. But if you have not, it should be fairly straightforward. For what concerns this, which is probably the weirdest part of these 3 lines, we're also giving explicitly the type of the type constructor itself. So in Haskell, this is not necessary, but what really will happen is that nat is of kind, they call kinds in Haskell, so nat is of kind star. The things of kind star are the types inhabited by values, right? So nat is something that contains the natural numbers. In Agda land, star is called set. The situation has been more complicated in regards with that, but for the time being, you can see it as star in Haskell. So yes. Obviously, we can write functions with working on natural numbers. So we'll define addition, which will allow me to introduce various features. So first, the syntax. In Haskell, we only have one kind of operators. Well, one type of syntax for operators, addition, right? And we refer to infix operators with these parentheses. And we have a very restricted set of symbols to pick from to define our operators. In Agda, we have an incredibly liberal syntax to write operators. So what we do is that we write the name of the operator with underscores where the arguments are. So we can write, for example, a unary prefix operator like minus, or we can even write if, then, else, and this is a valid operator. So we can do really crazy stuff, and it's really prone to obfuscation. And they're not shy about obfuscating the standard library with these features. So I'm not going to go down that path, but you can do really crazy stuff. The other thing, so in this case, it's a simple infix binary operator. The other thing that is new is this green thing here. I've actually typed this to get that, and then loaded the file. What this is called is a typo, which is something which is so cool that it's coming to Haskell as well in GHC 7.8. But they're still cooler because of Emacs and because of other features. So typos are placeholders that tell you, I haven't implemented this yet. I'm waiting, I don't know, I'm thinking, I have to get coffee, I don't know. And you want to put something there, I'm waiting to write the body of this function, and I want to find out about what to do with that body. So for example, I can say, what type do you expect here? And that's the goal. So here, Agda will want a nat. And what things do we have in scope? And it tells us, well, we have an n of type nat, and we've got an m of type nat. But even better, we can do stuff in the whole. So one thing that I really like is to case split on an argument. So I'm going to tell Agda pattern match on m. And it does. And here we've got the 2 data constructors, 0 and sac, right? 0 plus n is n. If we've got m, if m is a successor, we recurse down. We refine the whole with the sac data constructor, and then we call plus recursively. So this is kind of cool. I mean, when you've got big data types, being able to case split this easily is very neat. So I'm going to load kind of checkpoints. I've put here these pragmas, which basically let us use number literals for natural numbers. Agda doesn't have type classes, but I don't want to make comments on the philosophy of Agda, but I'm not sure they'll ever come to Agda, but they're not there yet. So we need to use this kind of pragmas to use literals. So we can, for example, ask Agda, what's the type of 3, and we'll get nat. We can evaluate 3 plus 11, and we'll get 14, and so on. So we can use literals to represent numbers. Let's do something slightly more complicated, but still doable in Haskell. Let's define lists. So lists in Haskell would be defined like this. Let's say nil cons a list A. So this is what you get, the square bracket type. And what's happening here is that list is parametric over this A, right? So this A is a parameter to the list type constructor. And list is of kind star to star. So it takes a type and returns another type. In Agda, like before, we need to put down this information much more explicitly. So we're telling Agda we've got a parameter, which is a type. And this is what set is saying. So it's of type set, which is the type of types. And then it's a type. Well, once we have an A in there, list A is a type itself. Once we have this, we can define an empty list and a const cell. A, list A, list A. Again, we're writing the type signatures for the data constructors explicitly here. Another note about the syntax, open square bracket, close square bracket is a perfectly good identifier in Agda, which is not the case in Haskell. In general, yes, it's much more liberal. Unicode symbols are fine. And again, they're not only fine, they love them. So there are facilities in the Emacs mode to input these Unicode symbols. And I won't be using many of them. But yeah, in the standard library, you find a lot of Unicode. We can obviously also write, let me delete this. We can also obviously write functions that are polymorphic. So in this case, it will look like this. Now, in Haskell, what we will have, list A. No. So in Haskell, the interesting part here is this A. In Haskell, this A is brought into scope at some point in that type signature. So it is a variable, right? It's not a constant. But the act of bringing it into scope is implicit. We don't see it. We can actually, in modern Haskell, do it sort of explicitly and say for all A, list A nat, which says, well, for any type, this function is going to work over lists. But it's still kind of a special thing, right? You have a different syntax, and most importantly, this A is always going to be instantiated automatically. The compiler will fill this in for you when you pass a list of some type, and will automatically infer what A is. In Agda, Agda treats types in a much more uniform way. So we have A that it is an argument like any other. It's an argument to the function length. But we do not want to provide the type of the elements each time explicitly. So what we can do with these curly braces is instruct Agda to infer the A. So when we pass in a list of natural numbers, it will automatically instantiate the A to be nat. So we kind of have the same effect that we have automatically in Haskell. Now in Agda's situation, why doesn't Agda do this automatically? Because Agda's type system is much more powerful and expressive, so there is no general scheme of, type inference is undecidable. But in general, finding a compromise for this sort of situations, it's harder than giving the user the tools to facilitate inference, like in this case. So again, I'm going to go ahead and define length, pattern match on excess, empty list is of length 0, non-empty list is of the length of the tail plus 1. Right, so again, this is all doable in Haskell, but it's kind of to see how we do things in Agda. Now let's do something we cannot do in Haskell. So because Haskell types are just not good enough, right? So like Agda and other languages are often grouped under the umbrella of dependent types, which is a very charged word these days. So I'm going to show you an instance of that. Dependent types means that types can depend on values. So that's what the dependent indicates. And the example for dependent types is lists, which carry their length at the type level. So we can avoid out-of-bounds exceptions and things like this. We can reason about their length statically. And these structures are usually called vectors. So I'm going to call them vec. Like lists, they accept a parameter indicating the type of the elements. Unlike lists, though, they also have an index. I'm going to explain what an index is in a second. But what's there to notice here is that in the two past data types, the thing to the right of the column was set. What we have here instead is a function into set. So this kind of is an instance, in a way, of dependent types, because the second parameter of vec is a value, it's not a type. In Haskell, we cannot have this. In Haskell, when we define a type constructor, all the parameters are going to be types, while here we've got natural numbers. Okay? And this parameter to vec is going to be the length of the list. So I'm going to define the data constructors so that this kind of expectation is matched. And the reason why I've put it on the right, the reason why I've put it as a function here and not to the left, is that in Agda, the things to the left must be the same across all data constructors. So this parameter, for example, in lists, this parameter A must appear as an argument of all the return types of the data constructors. This is kind of a detail of how Agda chooses to express this, but it makes things easier, both for the implementer of Agda and also for the user, I think. I mean, it's debatable, but that's how it works. So an empty vector is going to contain, well, it's going to be vec A, and we need it to be A, as I said. And it's going to be of length 0, right? All right, I forgot to mention, like, on the other hand, indices can vary across data constructors. So for example, here we're putting 0. If we add n napped instead, like A, we will get, Agda will complain, wait a second, this is not n. You cannot put this, you have to put n there. So let's go back to the right way. Okay, so the length of an empty vector is going to be 0. The length of a const cell, well, we've got an element at the head. We've got, we've got a vector of length n, and here I'm quantifying over the length of the tail. Okay? So this parameter to the type constructor is implicit, much like the parameter of length, because it can be inferred when we pass the vector in. So this is saying a const cell has got an element, it's got a tail of some length n. When you put them together, the resulting length will be n plus 1, which makes sense, right? I also forgot to mention another syntactic shortcut. If the type of the parameter itself can be inferred by looking later, by looking at its surrounding, we can tell Agda to do so by putting this for all. So we don't need to say that this is a natural number. So again, it's a shortcut. Another thing to notice is that I'm reusing the constructor names. Because Agda uses, well, Agda lets us do that because it looks at what type it's expecting, and so it resolves which constructor it is by looking at what type you're expecting. So this is something which is useful. Again, it causes confusion sometimes, but yeah, and this is the list of the confusion. So what can we do with these vectors? Well, a short example, which I think is very, you can relate to it, is to define a safe head function. So head in Haskell is not safe, right? So this is a GHCI prompt. I have an empty list. It crashes the program. We do not want that. I mean, we like to avoid that. We like to avoid these mistakes. So because we like types, right? So we can do this in Agda. And again, I'm implicitly quantifying over the type of the element and the length. So we want to accept only input which is not empty. How can we do this? Well, if the input is non-empty, its length is going to be non-zero, right? So we can do this by forcing the index to be the successor of some number. Because all numbers are successors of some number apart from 0. So this kind of expresses what we expect from the input. We want the input to be non-empty, which is what this is telling us, basically. Once we have our argument here, we can ask Agda to pattern match on it, and something really cool will happen. It doesn't even put the empty list case in. And the reason why Agda understands this is that it looks at this suck n here, it checks every constructor, it tries to unify this suck with the 0 here, it realizes that that's not possible, and so it lets us leave out the empty list case. So we get only the case in which the list is not empty, and we can return x. By the way, if you have any questions, I prefer to kind of write less code, but be clear, so please interrupt me. Yes? Right, so head is nice, but the real goal that we have with vectors for this code is to index into them. So we want to safely take elements out of a vector. And so we need some notion of number smaller than another number, smaller than the length of the vector in this case. We want to be able to be sure that the index provided by the user is less than the length of the vector. Because again, in Haskell, we can do 1, 2, can demand the fifth element of this list, and it's going to index to large, right? We want to avoid these situations. And there are many ways to go at this, but I think that the best way is to define another data type that expresses the notion of a number smaller than some other number. I'm going to call this fin, again following the naming conventions that are already there. And this fin, like vectors, is going to be indexed by a natural number. This number expressing the upper bound, the strict upper bound that we have. So fin, if we've got fin n, we want it to be the type of numbers less than n. And again, this is a dependent type in the sense that we've got a value here. Now, what is 0 less than? Well, 0 is less than anything apart from 0 itself. So we can use the same trick that we use with head and force the index to be a successor of something. If we've got an existing fin n, so we've got a number that we know is less than n, what's the biggest such number? N minus 1. If we take the successor of n minus 1, we're going to get n. So to make sure that the index is indeed greater than all the possible numbers here, we're going to increment the upper bound here, and we're going to be safe. So, for example, well, I mean, for example, we can have fin 3, and 0 is going to be fine. Such 0 is going to be fine. This is not going to be fine. Actually, this is not fine for the wrong reason. Okay, this is still fine. Sorry. But this is not, because we've got one suck too many. So we have now we have the right tools to define our indexing function. So I'll call it bang, and it will accept a vector of length n and a number less than the length, and it's going to get back an element of type. Yes, sorry. The pragmas are up here. Thank you. So, yeah, if I'm looking at the laptop, just shout something, and yes. So we've got our vector xs, and we've got our index x. I'm putting a hole here. So this is the index we're using. I'm going to pattern match on it. If the index is 0, we want the first element of the list. So we're going to pattern match on the list. And again, we're not going to have the empty list case, because 0 forces the n to be the successor of something. So we can return x. If the number is a successor of something, we pattern match again on the list, and again, we don't have the empty list case for the same reason. And we recurse down by indexing by the new index. So we take the tail and the new number, and we recurse down. So again, we've done very elegantly, I think, something which is quite cool. So we can handle. This obviously comes at a cost, because you need to carry around evidence that your list is, of a certain length. But it expresses very naturally, I think, this fact at the type level. Right. So now that we have these tools, I've also defined a function which goes from fin n to natural numbers. So it kind of simply forgets the information that the number is less than another given number. And now that we have these tools, we can finally move on to writing our language and our type checker. And I've got a small set of slides to present it. So this is, well, I don't know how familiar you are with this kind of syntax, but simple BNF kind of thing. And the language that we're going to use is a typed lambda calculus. Even if you've never heard or read about lambda calculus, it's not important. I mean, if you've been using Haskell, you're using a very powerful lambda calculus. But this is much simpler. And this language, well, we've got variables, which are simply denoting with x here. These are kind of variable names. We've got function application. This is the function, this is the argument, separated by a space, like in Haskell. We've got lambda functions. This is the argument name, and this is the argument type. So it is explicitly typed, not unlike Haskell, where we can omit the type. And we also have number literals. So this n here, it's purple. You probably can't see the purple, but we can kind of write numbers into our language. And we also have addition, so we can add terms together. And the types that we have in our language, it's very simple. We just have natural numbers. So literals are going to be of type nat, presumably. And we have the type of functions. So I'm using this double arrow just to avoid confusion with Agda's or Haskell arrow. So this is the type of the argument, and this is the type of the return type. The problem is that I haven't really explained what these x's are, but in programming languages you always have names of some kind because humans work really well with names. So, but when working with these kind of languages and manipulating terms, it's often more useful to use a more direct way of representing bindings. And the way I'm going to use, which is kind of the older probably way, is to use the Brownian indices. And the Brownian indices replace names by numbers. And what the numbers tell you is which lambda the variable refers to. So for example, if we've got this identity function, so we've got lambda x goes to x, so a very simple function, this will be simply represented by lambda 0. So we don't name the argument. We simply use the 0 to say it's the first lambda going to the left. If we have a constant function, so it discards the second argument, we've got lambda x goes to lambda y goes to x, we're going to have two lambdas binding two things, and then 1, because x refers to the second lambda going to the left. I also got a more complicated example, but you hopefully get the idea. So you've got lambda x goes to lambda y goes to lambda z goes to, this is the S combinator, but x applied to z applied to y applied to z. So you've got x, the third lambda, so 2, z, the first lambda, so 0, 1, the middle lambda, and then 0 again. So this is horrible for humans. You will never write a programming language using this as an interface. But it's useful to manipulate terms and prove things about terms and do all sorts of stuff with terms. So I'm going to use this convention. And by the way, when you're parsing a language, you can very easily transform from names to nameless. So it's not a big deal even when you actually want to implement a language. Again, I'm not saying this is the best thing. For example, Agda itself is not implemented like this. It uses names, but in our case, it's a good way of expressing this. So to revise our language without names, we're going to have, I'm calling it V, but this is going to be an index. This is going to be a natural number. And lambda functions are not going to have named arguments. They're just going to have the type of the argument, but we don't need to name the argument explicitly. Right, so with this idea in mind, we can define two data types. One for the types of our language. So it's either nat or functions. Function, argument, return type. And we can define the syntax of our language. So it's going to be either a variable, which is an index, so a number as we said, or function application. I'm using this kind of middle dot because I obviously can't use a space. So this is the function, this is the argument. Then we have lambdas. So there's a type of the argument, the body of the function. Number literals, that again, they're natural numbers. And additions. So the left-hand side and the right-hand side And yeah. So this is a fairly straightforward translation of what we had on the slide, right? But giving actual meaning to this V and to this N. The font bigger, yes. Is this better?
Yeah.
Yes? Okay. Right, so now that we have these elements, we want to write a type checker. And to write a type checker, we need to know what the type system is like. And this is probably the most scary slide, but I mean, it's really not. It's really not that complicated. I think it's the most concise way of putting the type system down. Even if you've never seen these derivations, it's really simple. So this says, if what's above the bar holds, then what's below the bar holds. And these capital gammas represent contexts. Contexts store the types of variables that are bound. So if we have a lambda function and we're type checking the body, we need a way to recover, to know what the type of the bound variable is. And by the way, this is a very popular convention. So if you read any paper, they use capital gamma and they use this syntax. So it's useful to know how to read this. So for variables, so keep in mind, again, that the context holds the types of the bound variables. So if we need to type check a variable, we look up its type in the context. I haven't defined what this consists of yet, but I will soon. Number literal are the easiest. That's simply of type nat. If we've got a term t, and if we've got terms t and u, both of type nat, we can add them together and get a new term of type nat. If we've got a function of type sigma to tau and an argument of type sigma, then we can apply u to t and get something of type tau out. And this is probably the most obscure rule now, but if we've got that t is of type tau in the context with augmented with sigma, then we can form a lambda function with sigma as an argument and t as a body of type sigma to tau. So this is basically saying if t with the new variable type sigma in is of type tau, we can form a function with t being the body. Right, now in Haskell, we'll probably proceed now to write a function of the type syntax to maybe type or something like this. So maybe representing the fact that it might not type check, right? In Agda, we can do much better. So the problem with this, there is no particular problem with this. You can go along with this and you can write a compiler, you can do awesome stuff. But if we have these facilities that Agda gives you, you can actually return something that not only returns the type disconnected from the input. You can actually return a structure that represents both the structure of the term and the type information at the same time. So you can break this information around and do stuff with it. So if we get to the optimization part, we can use the fact that the terms have types to kind of embed them into Agda and do stuff like this. So what we're going to do now is define a data type that expresses this. So a term with a type attached. And to do this, we're going to define, I need to define what contexts are first. So I've used gamma here, and I know I'm using indices for variables, and we have vectors. So a good idea would be to simply have vectors for contexts. So not only, we have a list in which we can index into, but we also have the length information, so we can have that extra safety that we'll need later. So I'll simply define context to be a vector of types. I can type this explicitly. So. Okay, so now that we have this, we can define our checked term type, and I've called it term. And it's parameterized over some context gamma. And most importantly, it's indexed by the type of the term that it contains. So this is where kind of the information is brought at the type level. So if we have a variable, so each constructor will give rise to different types. Number literals will have type nat, and function will be of an arrow type, and so on. So we can get the easy case first. So a number literal will be a nat, and it will be a term in gamma of type nat. Simple. conditions will take two terms of type nat and give a new term of type nat. This comes directly from this line here. So this and yes, the second and the third. Now, for what concerns variables, nat will not do because we will not be sure that it's going to be in scope. It might be bigger than the context. It might be an index that it's more than the lambdas that we've gone past. So what we can do is to have a fin n, right? Which serves just right because it's going to guarantee that the index that we have is in the scope of the context. Moreover, and this is the first time I do this, but this is probably like the central construct of dependent types, we can quantify over this, well, I've done it, but not kind of, yes. But we can quantify over this variable here. And when I find myself to define what the type of this variable would be, well, I simply look it up in the context, right? So I can do gamma bang v, and this is going to be the type of the variable. So here I'm using a previous argument later in the type. This is another thing you can't do in Haskell. The only arguments that you can use later are types. Right, so these are variables. Then we have function application. So if we have a term of type tau to sigma, so a function from tau to sigma, and an argument of type tau, we get out something of type sigma. Right? Yes. And finally, for what concerns lambdas, we have the type of the argument, let's say tau, and a body in the context with tau added of type sigma. Then we can take that term to be the body of the function, and we get out a term in gamma from tau to sigma. And so that's it. We've kind of represented, well, this is a way of representing a term including these typing rules in a way that guarantees that if we've got something of type term gamma some type, we can unpack it, and each subterm is going to have evidence that it is well typed. Right, we can finally move on to actually write a type checking function. I've also defined something similar to toNat, but for our terms. So this throws away the type information and goes back to a piece of syntax. This function looks really stupid, obviously, but well, it's not entirely stupid because you've got this, but it's yeah, it's sort of boilerplate. So I haven't taken the time to type it in now, but yes, it just throws away the type information and gets back to the raw syntax. Now we face another doubt. So we could simply define our type checking function to return some term of some type. But again, we can be more precise. So we can force the output to be the same term but type checked as the input. So we can express the fact that we're type checking a term and return that term but type checked. So that we're not modifying it, we're returning the checking of that term. And to do this, we're going to define another data type, and this is a common pattern in Agda. I'll call it check, and it is parameterized over context as well, and indexed over a piece of syntax. So this pattern, I'm not sure, well, I think they're called views, but so what you do is that when you need to write a function where the output has some relationship to the input, which is the case here, because the output is the input term but type checked, we have a term, we have a data type with the input as an index. So this syntax index here is going to be the term to be type checked. And so we can put constraints on it. And in this case, the constraints is going to be that the type checked term, the type checked term erasure is the input. So writing this down, if we succeed in type checking, so I'll call it yes, the kind of good case, we're going to return a type, a term t of that type. And this is going to be check gamma erase t. And this is the crucial part. So when we're going to define a type checking function, we will be able to force the output term to be related to the input term in the right way. If we fail, here I'm kind of going against my own principles. I let the user escape with any syntax. So we can kind of fail at any time. And this is slightly bad because this doesn't bring evidence that the input term is not well typed. If we had more time, we would actually have check to bring this evidence as well. So the type will be even more precise. And I want to stress that this is not only, this is useful to have correct programs, but it's also incredibly useful to write the programs. Because as we will see, especially with the tools that Agda gives us and tools in general, the fact that you have such precise types, the functions basically write themselves once you write the skeleton of the function. So we'll see various instances of that. But it's not only for safety. I think that it's also for tooling and to write software more easily in a way, once you get the types right. So our type checking function finally will be over some context gamma. It will take some piece of syntax as input, and we return check gamma t. Okay? So in this case, when we will return a term, it will be a type check version of this piece of syntax. All right, so let's pattern match on t. I'm going to leave out these two cases because they're the hard ones. So let's do the easier ones first. The easiest one is this. And look, I know that this is going to go fine, right? Because literals are always well typed. I say that this is going to be a yes. Then I tell Agda, just you do it. And it does. Okay? And we're able to do this because I was precise enough in the yes constructor. If we've got additions, we have to pattern match both t, type check both t and u. And the way we do this in Agda is with a with clause. So a with clause is sort of like a where clause in Haskell. So you're kind of naming an intermediate computation, but it's much more powerful. So it enables a very powerful version of pattern matching that we're going to see now. So here we've got P1 and P2, that there are the intermediate, that there is also type checking T and U. What we want those to be is two yeses, telling us that the type of T and the type of U is nat. We want them both to be natural numbers. So we can pattern match on P1, and something weird happens. So, well, we're getting a lot of goals, but also Agda here, we're pattern matching on the yes. And when this happens, Agda knows that the input must be the erasure of this result here. So what this is doing, this is called a dotted pattern. And what this is indicating is the relationship between the output of this computation and the original input of the function. Okay? So this is not a variable, and it's on the left-hand side. This is something else that doesn't exist in Haskell. And this is very powerful, not only for us humans to understand what's going on, but also for type checking. So the type checker knows this as well. And this lets us write these kind of functions much more quickly. It's hard to realize how good this is until you try the alternatives, when you have to kind of do these things explicitly. So I'll pattern match on P2 as well. I'll actually just eliminate the other cases because they're wrong. We want both types to be nat. I'm just going to rename this to U. And again, this is correct. And you do it. Good. So what we get is something of type nat and the type check term in the yes constructor. Finally, slightly harder, lambdas. We've got another with clause checking the body of the lambda, but we add the type of the argument to the context, just like in the type row. So we've got some intermediate result here. We pattern match on it. If it goes wrong, then the top level thing goes wrong too. If it doesn't, then we've got, this is going to be the type of the body, and this is the type of the argument. But Agda, we don't need humans for this. Done. Okay, so it automatically inferred that this is going to be a function type, and it put it there by itself. So yes, so I think this is pretty cool. And without dependent type, without precise types, you cannot have this tooling. So it's that's the interesting thing that people, I mean, people focus on the maths, but I think this is equally cool, that you can have really incredible kind of IDEs with this kind of types. Right, so what's the problem with variables and applications? Where for variables, what we have here, we can ask Agda what we have here. We've got a v, which is a natural number. Okay. What we want to get, however, is a fin n. If we go back to the definition for type check term, because we want to know that the variable is in scope. So we need to convert this natural number to a fin n. And this might fail because it might be too big. So we're basically doing a scope check here. So we need some additional tools. And to write these additional tools, I'm going to use another view. I'm going to call it from nat. So what this does is that it's parameterized over the upper bound, so over the n here, in the, well, the n, which is going to be the argument to fin, right? So this is the length of the context in this case. And indexed over the input indexed over the number that we want to convert. So this is, again, the same pattern of indexing over the inputs, because we will be able to constrain what the input is, depending on the constructors. So if this succeeds, we're going to get a fin n, which is what we want. And we're going to force that fin n, the erasure of that fin n, to be the input. So this forces the two numbers to be the same, but this new number has got that additional type information. If this fails, we're going to get a number which represents how much out of bounds we are. And we can assure that this is the case by forcing the input to be n, so the upper bound, plus m. So this is, right, so this expresses the fact that the input is bigger than the upper bound. Once we have this view, we can write a function. So we've got the upper bound, and we've got the, our number, and we want back a from nat and m. And this is probably the neatest example of just the function writing itself. So, right, so let's pattern match on the bound. If the bound is 0, we have no chance. The bound is 0, m is not going to be less than 0. So we ask Agda to try to do it automatically, and it says no m. M is the offset. M is how much it goes past the upper bound, because the upper bound is 0. So whatever m is, that's going to be the offset. If the upper bound is a successor, we pattern match on m as well. And if m is 0, we've done, because we know that it's going to be less than suc n, whatever n is. And again, Agda understands this. If they're both successor, then we recurse down. And you can really see the patterns here of recursion. And we've got two intermediate results again. And what did I do here? That salmon is not good. And
It's wrong.
It's not true, right? This is structural. Yeah, disregard that. But
Oh, wait, no. You just need Haskell parameters.
huh?
You only Haskell parameters. Like, so
Oh, yes, of course. Thank you. So yeah, why not? This is nonsense. Yes. Of course. Yeah.
You've got about 5 minutes.
Yeah, I'm almost done.
Okay, so just a warning, you're pretty strict about time.
Yeah. I'm almost done. And I'm missing. Yes. So we pattern match on the result. If the result goes well, again, it can infer everything by itself. And we can finally write this, the type checking for the variable. So here we're taking the argument explicitly. Well, we're taking the length of the context. We're putting it in scope here. We try to convert the variable, the natural number, to a fin. Again, yes, I have to go a bit fast now. We see if that succeeded. Again. We see if that succeeded. If it did, then we've got a well-typed term. And look how it even, it even put automatically the fact that the type is looking. We have to look up in the context to get the type. I didn't write that. If converting fails, we put no. And finally, and I'm going to do this really fast because we don't have much time, we need to type check applications. And the problem here is even a bit subtler, I think. So first we check both sides, just like we did with additions. So if it fails, we would know here. Not only we would know, but we want the thing on the left to be a function type. So we pattern match like this, and this is going to be some other type here. Right, so what's the problem? Here we've got tau and tau prime. So we've got the function which is of type tau to sigma, and the argument of type tau prime. But we want to know whether tau and tau prime are the same thing. To do this, we need to have some kind of equality procedure for types. But we need to express the notion of equality at the type level to force the Agda type checker to understand that if tau and tau prime are equal, they're actually the same thing. And the way we can do this is by defining.
I'm sorry,
Yeah.
you don't have time to do type level.
No, but I mean, yeah, okay. I wasn't going to, yeah, because I started 10 minutes late, so that's why. But I can skip this, but. Yes.
Just jump ahead and people can look at it.
Yeah, so what you do is that you define an equal data type, parameterized over one type and indexed by another one. And the yes constructor is going to force them to be the same by having the index to be the same as the parameter. And then you have this equality procedure to tell you if the types are equal or not. And again, I'm being a bit sloppy here. But yeah, I don't have time to explain that nicely. And you can write a more general version of this. But equality is a huge, you could have 10 lectures on equality. So, yeah. Okay, so I guess I'll find it here. Well, the conclusion is that even if it might not be entirely clear here, by having precise types, we can gain we can gain a lot. We can gain, of course, correctness, so we can certify our programs in a quick way. But we can also gain a better understanding, both ourselves and the tools that we use, of the programs we write. And this allows for a lot of expressiveness, for very interesting programming, I find. Then, of course, that's an opinion, but I think they're going to go very far with this. So. Thank you.
Okay, so yeah, thanks for a great talk. I'm sorry I don't think we have time for questions, and I know there's so much more you could do that would be really interesting too. We have to get out of here quickly. Couple quick announcements again, want to run over. Next meetup is going to be early October in a different location. We'll have that information. I got an email from Dustin. We will be doing a homotopy type theory reading group in collaboration with some of the mathematics people at CUNY for people that are interested in tackling that homotopy type theory book together. The first meetup, they're going to be alternate Thursdays, probably starting on September 19th, and I'll send all that information to the list. So that's coming up. Oh yes, if you want to work in a functional environment but are okay not getting to do anything but .NET and SQL largely, come talk to me. And we have Doug, who's got a couple of announcements about the bar.
So as usual, we're going to go socialize a little bit at Central Bar. It's on 9th Street between 3rd and 4th. few blocks south, 1 or 2 blocks east. See you there. Just really quickly, I've had a couple of people tell me that they were interested in more presentations about Snap. I'm one of the authors of the Snap Web Framework. We don't really want to pollute this particular meetup with talk upon talk of Snap, but just show of hands, if anyone is interested in like a Snap meetup, then raise your hand and we'll think about it. 1, 2. Okay, thank you very much. Well, I will get back to you on more. We'll see what we can figure out. Have a good evening. We got to get out of here quick, so leave.